Okay, so I guess the point where we left off was this idea that we all have like a flexible part to our own way of designing. But again, the point of technology, I think that people are here studying at UPC, but also that we try to achieve in tech companies is to address the fixed part. So the fixed part, again, just to be clear, to set ourselves back into what we were saying before, try to keep a straight face. I think, yes, what we were saying is there's a flexible part to our expertise. Again, remember, so flexible part is our own style, our own way to do architecture. The fixed part is our expertise, is the method, the way we try to shape a common understanding of the discipline. And that's what we go to learn at school. That's what we share on the job site. This I've already told you. And so it's this common methodology that technology actually tries to address. It's this shared belief that we try to assist with technological tools. And this is where really parametricism that but also AI steps in and can help maybe. And in fact, that history, or that notion that there's a fixed part, right, to our expertise, and that there's then a methodology, a form of systematization of rules, of methodology, of common belief, that actually has an history. If you only look back at the past 100 years, you see 4 clear movements that have shaped the systematization of our discipline. Or let's just say there's a common thread, a common history of trying to think about a methodology for our discipline. We can see at least 4 great movements that are special to our discipline. That are modularity in the 30s, then computational design, what you know as CAD, that started in the 60s, then parametricism that you all know in the 90s, and then AI that is, I think, starting to emerge today in our discipline. But anyway, those 4 movements simply underpin this continuation, this gradual increase in systematization, or let's just say the consolidation of a common methodology for architecture. So again, AI is not a disruption. It's not this thing that is coming out of nowhere and falling onto us, but rather it's just the continuation of something that started a while ago, and that actually borrows to all the previous movements that came before us. So I think it's healthy just to remind ourselves of that, because often AI is seen as like a disruptor coming from outside that is, like a stranger to our way of thinking, and actually it's closely tied to things that we are used to. So again, it's not a disruption; it's a new thing, but again connected to what we know, and understanding the connection between AI and the past of our discipline is the key to understanding what it brings to our discipline. So before talking about AI, I think we just need to step back, rewind a bit, and understand where we are at today, and then think about AI as something that complements the shortcomings of our current period, and maybe, only maybe, allows us to go forward. So where we are at today is what you all are, that you are studying today in your master, is parametricism. It's this notion that we can parametrically define design. So before talking about AI, I think we should coin down together at least a definition of parametricism and be very clear about where we are at today, where we stand. So parametricism, in fact, simply states the following thing, is that to any design process, I can declare a set of rules and a set of decisions that go from one rule to the next that can, by the end, discretize the notion of design. So this very weird diagram you see on the slide simply shows how to go from the beginning of a design process all the way to the end to lay out an HVAC system. So it's just a series of steps. Those are like the geometrical shapes, and a series of decisions, arrows going from one to the next. And this is, by essence, what parametricism brought at the very beginning. It was to say, well, to any design process, I can discretize that process into, again, decisions and steps. But again, parametricism went one step ahead of that idea, and this is what you're all familiar with already. But in parametricism, you can also hook a parameter to each decision to make each decision vary, and then by the end to obtain different options, of course, based on the parameters that you've set for each decision. So that process of decision, rules and decision, and then parameters hooked on this was a way to first discretize the design process, but also replicate the variability of options that a given process can yield. If I change the parameters, I get different options by the end. Well, this simply gives us this idea that there's not one single output to a design process. There's a multiplicity of outputs. And again, parameters are here to modulate that reality. But there were two things that parametricism could not tackle, could not explain. When you declare a script, when you come up with what we call a procedure, so again, any script that you can code in Grasshopper is ultimately a procedure, a series of steps. To any procedure corresponds a scope and corresponds, let's say, a narrowed down place of the problem space. To choose is to restrict, this motto. It's especially true in parametricism. The more you define procedure, the more you narrow the scope of potential option you can get by the end. But also, balancing the parameters becomes a challenge. It's not just a matter of scoping the problem, it's also a matter of finding the best answer, meaning tweaking the parameters to get the best balance. So ultimately, there were two questions that parametricism felt short to answer. The first one is my script holistic? And the second one is my script relevant? So to be clear, is my script holistic simply means once I've defined a procedure, how do I know whether I've scoped the problem the right way? Whether the realm of potential option I can get by the end is the right one for the problem I'm trying to model. The second problem is my script relevant? Meaning, did I find a relevant answer? Have I balanced the parameters in such a way that I'm getting the most relevant potential option by the end of my procedure? So as you maybe already know, for a hard design task, it gets really hard to discretize the process. You end up declaring procedures, scripts that are almost endless, and balancing the parameters can often be really tricky because it leaves you into a multi-dimensional space that has too many dimensions for us to really balance. Therefore, we helped ourselves using optimization. And a common practice, something I experienced at Lausanne, but also in my early on in my studies, is that facing too many parameters, we simply dump all those parameters into an optimizer. Some of you might be, you might know Galapagos, which is a way in Grasshopper to optimize and balance parameters. Well, you simply give all those parameters to an optimizer and hope for the best. But again, you often get stuck in what we call local optimum, meaning among all the options you could have found, among all the the balance of parameters you could have gotten, you don't know really whether you found the best option, or at least the best spot in the problem space. You're often stuck at a local solution, meaning something that is suboptimal. And again, suboptimal means, well, it's good, but it could be way better if you would have had the opportunity to browse even more into the problem space. But again, optimization, falls short sometimes of giving us the best potential option. And also, design is a really hard problem to simply discretize. So it's really hard to declare the procedure. Therefore, it's really hard for the optimizer to walk into the problem space and really give us the best potential option. So two clear shortcomings: is my script holistic? Is my script relevant? I'm not saying parametricism is not solving things for us every day. It really does. But there's so many questions in the design disciplines that can't be simply discretized the way we do it in parametricism. So what AI is simply a way to find an alternative solution or alternative set of methodology to tackle those hard questions that could not quite be coined down by parametricism yesterday. So to understand AI, we need at least to understand the notion of statistics. Some of you might already be familiar with the notion, but I think it's just healthy to remind ourselves of what it is. Statistics and statistical modeling simply says, facing a phenomenon, a given phenomenon that I'm trying to model and to understand, instead of trying descriptively to say how this phenomenon works, which I was doing with parametricism, I'm rather going to look at observations, meaning I'm going to look at occurrences of the same phenomenon again and again and again, 1,000 times, 1,000,000 times. And I'm going to try to find the underpinning across all the observations, across all the occurrences I've seen of the phenomenon. What are the common characteristics, properties, common to all the observations I've made? What you see on the slide is what we call a statistical distribution. It's simply a way to give characteristics to thousands, millions of observations of a given phenomenon. Statistics, therefore, as you understand, embraces observation against description. Descriptive sciences really gave us today an amazing opportunity to handle complex phenomenon using mathematics, procedural algorithmics, and other tools that were great to model phenomena that we could potentially get by ourselves. But the thing is, there are so many phenomena that actually we can't really grasp in a descriptive fashion, and therefore statistics comes in and helps us coin down the properties and characteristics of those phenomena. I know I'm repeating myself here, but I just want to make sure that we get this idea that it's observation that we're talking about. It's not description anymore. It's really like a shift of perspective, a new approach, truly new approach. So this is the premise of AI, building an understanding of a phenomenon using statistics as a methodology to apprehend, to model the phenomenon. And so AI does a bit more than simply statistics. It does statistical learning, meaning it looks at a phenomenon and models it statistically, but it also refines its understanding of the phenomenon across time. That's what we call learning. Learning simply means, well, I'm going to look at examples of this phenomenon again and again and again, and I'm going to tweak progressively the weights. The weights are simply parameters of the model. But the model is going to tweak and change those parameters in a somewhat autonomous fashion. So this is to simply explain statistics and to roughly explain statistical learning. But now let's just jump into architecture and understand what this does for us. What you see here is a training sequence. So I was mentioning learning and statistical learning right before. Well, all the images you're going to see, or most of them are from my thesis at Harvard 2 years ago. And so what you see here is, again, the training sequence. So as you use an AI model, you basically, you want it to learn progressively the phenomenon. The phenomenon that I'm interested in here and that I was looking to for my thesis was the fact of drawing floor plans. So the floor plans I wanted the model to draw were simple images. I used colors to encode programs. So, green is the living room, red is the bedroom, etc., etc. And I would show to the model images of the plan, and let's say pairs of images. One would be the footprint of an apartment, and the other one would be the same footprint but filled with rooms. And what I wanted the model to learn is how to go from A to B, how to go from an empty footprint to a footprint filled with rooms as a fully furnished and layout apartment. And so what you see here is the sequence of images generated by the model during training, during the learning phase. So at the very beginning of the sequence, the model gets almost nothing. And by the end, it's able to draw a certain quality of floor plans. So here is a new image where we explode the sequence that we've seen before, and we just lay it out. And you see at the upper left corner, the training start, and bottom right corner, the training end. And so what you see here is that we can go from the beginning to the end, and progressively the model acquires certain features, understands how to draw the floor plan. When I say understand, I simply means models. I'm not saying grasps as we would do in a conscious fashion, of course. It's simply refining its ability to draw floor plans. And so if we go through the different frames, after like 20 minutes of the training process, the models generate a footprint that is empty. It's just the footprint of the apartment, but there's nothing inside. After 2 to 3 hours, it starts to generate floor plans, but this time with like this edge condition, which is the facade, right? This poché, black poché, is the facade of the apartment. And it's also starting to understand that we need to put program in there. So it's adding, a green patch, a red patch. That is to say, well, we need program in there. But the program makes no sense so far. Moving on, after 10 to 15 hours, we start to get, more piece of program, more elements of the program being pushed into the footprint. we also start to see partition walls in between program piece. At the same time, the model is trying to find the right adjacencies. It's trying to, put rooms next to one another so that it would make sense to circulate in the apartment afterwards. But it's not perfect at all. The ratio of the rooms is messed up. The adjacencies are not quite there yet. The last thing we do see here is that it's starting to learn constructive feature. For example, the notion that the facade is open. So on the left side, you see no walls. Well, that's the opening towards the outside. Also, it's starting to put columns here and there. Those black patch are actually columns, going through the space. So it's getting there. It's imperfect, but it's getting there. And then towards the end, after I think 20, 25 hours of training, well, here we are. So what we have is an initial guess of what a floor plan could be given the footprint condition. In red, you've got the bedroom. In green, the living room. You see that it's quite sensible. The dark blue patch is the corridor leading from the entrance to the kitchen in cyan in the center. And then you have, in purple, the bathrooms. It's not perfect. So that's what I'm going to say right now. It's not a perfect architectural floor plan. Not at all. But coming up with all the heuristics to handle for almost, I'm not saying any type, but almost any type of footprints, being able to put a program in there, coming up with the rules, the heuristics, descriptively encoding the rules would have been actually insanely hard. And there's almost more than 20 years of research already that has been poured into this problematic. And if you look at the state of research using descriptive techniques to do internal layouts, well, there were some results, of course, but it's not far from being perfect. And there's really ways to improve over the existing research with descriptive techniques. Here, using observation, using AI, we calling down real fast, actually, a model that can scale and adapt to changing footprints. It's not perfect, again, but it's really close to something that we could use as a first pass to then improve over. So now that we understand, in a tangible fashion, what AI does to architecture, why it's not just a marketing term, why it's actually something tangible, I think we can, jump ahead, and I'd like just to give you now three threads that represents things that AI brings to architecture, and that AI should bring even more in the future. Meaning, if you are planning to do research for your master, or in the future a PhD, or I don't know, well, you could pour time into one of those three things, and those three things are flexibility, options, and analysis. So those are three fields or three tangible contributions of AI to architecture. So let's just jump right in. So the first one is flexibility. So the idea of flexibility is simply to say, well, when I design and I make a building, well, I want to have some amount of flexibility. I would argue that most of the tools we have today try in some way to handle this reality. It's helping us solving hard things or tedious things so that we have more flexibility to design during the early phase of the design process. So what you see here are results of my thesis at the very beginning with the very early models I had trained. So if you look at the bottom left corner and upper right corner, you see a square. And so this is a very simple canonical shape, right? A square or rectangular shaped apartment. And what the model is doing is, given the footprint of the apartment, is infilling with partition walls. Okay, so it's really simple. It's an easy task, and the result is not too great, actually. But when I saw that at the very beginning, I thought, okay, fine. If it can handle those very easy footprints, maybe I can give it, well, tougher conditions, like circular footprints or ovoidal footprints, or even the one in the upper left corner that is way less easy, I think, to infill with layout. And the model is still able to go at it and find some amount of partitioning in there. So those partitioning you see here make absolutely no sense. So that's why I moved to with the same logic and using almost the same shapes, try to look into the notion of program, because program is already one step ahead. It's way more interesting and way harder than laying out partitions, because you lay the partitions and elements in space with respect to the program, and that is actually really hard to do. That's what architects struggle with on the job site. And even if it's not perfect, at the very beginning I was starting to see, well, it's possible to ask for complex shapes, and it can return an initial pass that is not perfect, but an initial guess, let's say. So what it does for you is that then you get so much more flexibility to design, because I could take really complex shapes and play with certain families of shapes that I could have never afforded before in my design, and have the model go at it and infill it with an apartment. I would tweak those apartments afterwards, of course, but again, the heavy lifting was being handled for me, and that led to in my thesis designing those buildings that had impossible shapes, and yet finding some amount of resolution in there. So this is the early results. Then those models got trained a bit better and packaged into an interface where on the left the user can input certain conditions. So in black, the footprint of the apartment, in red, the position of the windows, and in green, the position of the entrance door. And on the right, the model would return in real time an assumption, like a guess, how the space, given the condition on the left, could be furnished, the layout could look like. And it's not perfect, but those initial guesses were immensely useful when I then used those tools to design. So here is the notion of flexibility applied to floor plans. So during last semester, so from February up until June, I curated an exhibit in Paris called AI and Architecture, and it was one of the first exhibits in Europe, trying to show the intersection of architecture and AI. It worked pretty well. Then COVID shut the museum, unfortunately. So we went online and made a virtual exhibit that I'll be more than happy to share the link with you. And so in this exhibit, we were showing multiple applications of AI to architecture. So the example I'm showing here is from Danev and Müller, who are two professors at MIT, who in their lab, look into also this notion of flexibility. So the structure you see here, all are generated with some AI models, all answer the same brief and the same task of performing to a given standard. But then once those performance targets are met, their model is able to go across the problem space and grab all those options that correspond to the performance targets and yet are different in shape and size. So again, much more flexibility for you as you design a structure, because you can set those performance targets and then harvest so many options that answer the brief, and therefore as you use those complex forms, well, you can afford it because they do answer those performance targets. Another example is coming from Kai Steinfeld, who is professor at UC Berkeley in the US. He worked on a project that is, I think, quite amazing, that talks to the notion of representation in architecture. So all those images you see here were generated by models that were taking as input pictures of white cubes sitting on a white plane. The pictures were taken as if those cubes were buildings, so in a perspective view, and then the model would simply overlay a texture like above the image. So the white plane would become the street, it would add the trees, the cars, then the white cubes would be the buildings, so those cubes are here textured as buildings. But what you see is that the scenes it creates are they're not perfectly realistic, but they give you a first idea of the atmosphere of how would things be in this early massing you've just made. So he has a lot of research online and even more results recently. So feel free to check it out, because I think it's quite interesting. It does not really tackle the notion of performance, but it talks to the idea of representation in architecture. So we've seen for flexibility, it really assists you in the design process. But more than simply assisting you, it does what we call optioneering, but it's kind of a ugly word. But the idea is it provides you with options, options during the design process, and that's really it's a key thing. We in architectural practices we produce all those models. We strive to give the clients or other designers more options, catalog, as we say, it's a common word. Well, AI, thrives in that respect. It gives so many options that can really enrich the design process. So the models that were around during my thesis were those models where it was really hard to get multiple options for one. Actually, the models I used, those were supposed to give you what we call a one-to-one mapping. For one input, you would get one output, only one potential solution. Well, I was able to hack my way through the model, and then by the end, I could get up to 4 options for a given input. So the input is on the left, the outputs here are on the right. And so given the footprint, given the position of the window on the door, you would get those footprints here on the right. So it's interesting because you see that they don't diverge too much, but they do give some amount of variation. So it's a great thing, because as you design, you do want more options for you to fit into your process. I've done more work since then, and I presented actually at ETH a few weeks ago. The presentation is online if you want to watch it, where I explain how we can go past this into what is called like a latent architecture, which is like a embracing new types of AI models that have what we call a latent space. And this latent space can help you embrace what we call multimodality. So multimodality means for one input getting like loads of outputs. So recently I've worked on models that actually have way more options than those 4 I'm showing here. But that slide still exemplifies this idea. It's easy, it's feasible to get a lot of options for a given input, but also have control over those options and to be able to ensure the variety of options. You don't want to have 1,000 options that are all the same. You want to make sure they diverge. And that is also something you can account for as you use an AI model. So by the end, you could end up with like an array of floor plans during the design process. You could also generate, back to Kyle's work, in this case for the same input conditions, so many potential options. What is also interesting with Kyle's work is that the models were trained for given neighborhoods, so they had actually specific styles embedded in them. One would draw things as a forest, another one has a suburban city. So there are also ways to bias your model to get a lot of options, but also with respect to certain qualities. Thing I'm sure you've seen before, a model done by Isola and Al, a team of researchers at Berkeley, and they've worked on translating patches of colors as inputs into a fully textured facade. So again, another example of getting multiple options. So optioneering, feeding your design process with options is one thing. The last thing that we should, I think, touch upon is the notion of analysis. So I think it's something you all know pretty well. I think your master actually tackles this notion. I think there's a lot of structural work in your degree. Those structures have to perform, and simulating the performance, of course, a key concern. To be able to afford simulation and to keep in check the performance of a design, it can be sometimes very costly, long to parametrize, long to compute. Physics engine that we use usually, like finite elements, can be very hard and complex to put in place, and also very expensive to run. AI, however, offers, let's say, a shortcut to getting those performance in check while being able to afford, both in times and also in terms of money, those simulations. So there's a way with AI to democratize simulations. So specifically, this is work that has been done at Spacemaker Research. So on the right, what you see is, in black, those patches are the footprints of buildings into a neighborhood. And the colorish gradient in between the buildings is the diffusion of noise in the neighborhood, because there's a road passing by, and you want to know how much noise is going to go across the neighborhood. Well, that simulation takes 10 minutes to run with a classic process with a physics engine. On the right is the result of what we call a surrogate model. So a surrogate model is simply a fancy word to say a type of AI model. Well, once it's trained, it can do a prediction. It's never going to be as precise as a simulation engine. But again, we're not designing a plane or a car. We can afford to be a bit loose on the precision for the sake of time. So what you see is that the image on the right took 0.05 seconds to compute. And the tangible outcome of this is what you see on the left. It's what we call live analysis. As you change your design and a given massing, you can recompute the performance in real time. And it's actually a big deal. Because even though simulation all across our our discipline, when you talk to people on in the discipline, or especially in the industry, not so much in academia. I think in academia we have time and sometimes resources to look into those simulations. But at the end of the day, in the industry, it's not that easy to get those performance assessments, and therefore more often than not, people just don't do it, or just wait for the engineer to do it. Here we have the opportunity, using surrogate models, to do those shortcuts and to predict in real time the performance, and therefore to actually use performance simulations in our design process every day. So it's kind of a big deal. It's something that is more and more feasible. That actually is feasible with Spacemaker, but also, which is the case in other recent softwares or web apps. So analysis is the last one, and again, a third thread of research that if you're interested in, you could look into. And again, there's work in this area and research done with surrogate models to do that. So I think we should step back a sec, and besides just the contribution, bring back somehow the historical perspective into the discussion. Because you could really argue after this talk that AI could be simply another tool in an horizontal sequence of toolbox coming your way. So simply said, AI would not be a big deal at all. It would simply be a new hack, a new tool set, but nothing quite substantial, nothing quite paradigmatic. So the idea behind this discussion is the idea of progress. I mean, is there any progress in there? Are we moving forward, backwards? Are we stagnating? The discussion around progress is a really hard one. It's something that epistemologically we should be careful to discuss. However, the idea of progress in a given industry, in a given time frame, for a given purpose, can be articulated. We can discuss progress if we frame in time, in space, and also we frame the discipline where we try to see progress. Well, for us, progress would be, were there any progress in the systematization of architecture over the past 100 years? We know that it means the rise of computation. We know it means those four movements here: modularity, CAD, parametricism, and AI. We know where we stand, in which world we try to assess progress. What remains to be said, to coin down whether progress is actually happening, is what is progress for us. If we can do a simple mind experiment and think, okay, fine, when I use a computer, especially for generative design, let's say, what am I trying to achieve? You could argue that there's two dimensions to what you hope to see in the results that the machine gives you. You try to achieve a variety of options that are relevant. So variety and relevance, I would argue, are the two essential dimensions, the two essential criteria to judge whether the technologies we use actually perform well or not. Variety simply means quantity by singularity. So it means I want a lot of options that are singular, that are unique, that are different from one another. That is variety. The second notion, relevance, in our field is, well, architectural quality, architectural relevance versus constructive feasibility. Does this make sense architecturally? And then other things, can I build it? If you cross-reference variety and relevance, then you get progress. Those two, this progress metrics is saying, well, am I moving towards more variety and relevance in the thing I create with my computer, or am I, just declining with this respect? So if we take those two matrices, so bear with me, it's actually pretty simple. It's just a projection matrix. So there's the variety matrix on the left, the relevance matrix at the bottom. I'm simply placing on them the four movements we've seen: modularity, CAD, parametricism, and AI. It's as simple as this. So I've got articles online that explain why I'm putting them where they are. But if you place them that way, and then you project them on the progress matrix, the one that really tries to map progress, well, you do see some form of progress. So on the progress matrix, upper right corner, the bottom left corner is minus minus, worst case scenario. Upper right corner is plus plus, well, the best case scenario. And you do see that from modularity to CAD, to parametricism, to AI, we're moving forward towards more variety and more relevance in the things we create. So it's not a linear progress. It's not, this endless stream of progress that would have, never wavered, never changed. You know, it's a jagged edge, but at the same time, it's moving forward. And I think that's why when we talk about AI in our fields, it's something to get excited about, but also to understand kind of the historical purpose of this. Like, it's actually a big deal. It actually pushes the envelope, actually brings more relevance and more variety to the things we create. Therefore, it's worthwhile, or worth our while, to pour time into this. There's so many things you can create, so many prototypes you can hack. There's so many, you know, small things or big things you can do. But knowing that those things, you know, contribute to a broader picture, completely changes the taste of what you do every day. And so I think with AI, we can be, you know, somewhat confident that it actually pushes our discipline forward. It's not something that, you know, makes us regress in terms of variety or relevance or the thing we create. I do think it's pushing us forward and for the best. So I just want to leave you with a quote. It's just from a book I really like. I'm sure you know it, Letters from a Young Poet, Rainer Maria Rilke. The reason why actually we should care about all those things, AI, parametricism, all those ideas that, you know, buy into this vision of a systematization is that, well, for us to come up with systemic things, there has to be a system to be found. And that is kind of, I think, maybe a belief we share today. Maybe we don't, and we can discuss it. But with Rilke, there's this quote that is really nice, saying that in the depth, everything becomes a law. It simply means that if you look hard enough, long enough into a problem, you might actually be able to discern the law, the rules. But when it comes to AI, to this, again, these new things, well, it's just a way for us to remind ourselves that it's in the depth that there are laws, and it's pretty deep, especially when you come to design. It's not an easy, shallow problem. It's a deep topic. It's a profound topic. It's so deep, and it's actually so hard. Then back at parametricism, it's really hard to actually model the hard questions descriptively, to come up with the heuristics, to come up with the procedures explicitly. Not all problems can be done this way. And AI actually might help us, you know, bridge this gap and you know, reach through this depth to actually coin down those laws. Not all of them, of course, but some of them that at the moment we just can't answer with parametricism. So to wrap this talk, here are 6 publications or websites of things I've worked on in the past. Feel free to, you know, just scan this and go ahead and look into it. And then there's also the exhibit online. The link isn't here, but this AI and architecture exhibit is actually still up as a virtual exhibit. So if you want to check it out, I'm happy to share the link. It's like a virtual exhibit, so you can just go, you know, across the space of the museum, and it walks you through the history of AI in architecture. Then there's a few talks, then there are some applications, and then there's a book, of course. So with that, I think I'm on time, and I'm more than happy to take questions if there are any.
Perfect. Stanislas, thank you, because this presentation really, at least it blew my mind. So I hope that everybody else is asking himself or herself, how is this, how has it been done? Because, well, you have talked about the potentialities, but not about the technical details. I will leave, however, to our students to ask if they have any questions before proceeding. I think we have about 25 minutes, half an hour for questions. So let's have them first. If anybody wants to shoot first.
Hello.
Hello.
Hey.
Go ahead.
This is Luis. I was just wondering if there's some research or recent applications for the design of cities more, or you were saying about neighborhoods. So I think this will be super handy to the design of our cities in the future.
So moving up one scale, right, to this to the scale of the master plan rather than the scale of the building. Is that your question?
Yes.
Yeah, I know. So absolutely. So there's lots of work on this area actually. So it's really interesting because there's so many ways to model a city, and for that I mean to choose a data format to represent the city. So there's multiple avenues of where researchers have used AI to model a city. So there's been work done using pixel informations, meaning images of a city, to then generate other images of cities. There's also research that has been done using a graph approach. Can I model the city as a graph and then generate the street network using some AI models? So there's in this area, the discussion today is about the right data format to represent the city. In the exhibit, actually, let me just think. Actually, it's supposed to be in the book. Normally, in the book of the exhibit, there's a project by a professor from the Bauhaus who now works at ETH, Reinhard König, who worked on applications of AI applied to city planning. And I think it's really relevant. The one challenge, I guess, with city and city planning is that in fact the metadata, and when I say metadata, I mean the data that is not geometric, the data that lies that is bundled to the geometry, but that you can't see in the geometry, is way richer for a city than it is for a building. And so the big challenge with city planning using AI is collecting this data, structuring this data, because again, the amount of metadata to collect in order to generate relevant master plans is insane. But because it's hard, it's fascinating. It's really hard, but completely fascinating. And I've done some experiment in the area actually. The amazing avenue for us, like AI, machine learning, the big thing here is, where do I get clean data? The huge data tank repository for us is GIS data. So let's be very clear. There is so many shortcomings to our techniques in our industry. We even our Revit models, even our BIM models are dirty. But GIS data, because the software ArcGIS is so inflexible, the data is clean. Those shape files that you use in a GIS software, sorry, are very clean, and they do what I was talking about. They bundle loads of metadata to the geometry of buildings. Tapping into those shapefiles is a gold mine. Cities have actually open web portal onto which they upload those shapefiles. That is in itself an amazing repository of data, an insane amount of opportunity are lying down there to do what you were asking for, Luis, which is master planning. So if you're excited about this, I mean, even Barcelona has it's endless. New York, of course, loads. But again, I think you got the theoretical answer, and then for the more practical answer, GIS files are just, I think, great place to start to actually get running with this.
Thank you.
Welcome.
I have a question for you.
Sure.
My name is Rudy, by the way. I read your article, AI and Architecture.
Yeah.
I was interested because I always thought, I live in Lebanon, so
yeah.
I always thought, why won't we create a software that will create let's say there are so many laws in architecture, how much the opening of the windows, if you can put the window in this direction or no, as the limit. There's so many laws. So I was always thinking, why won't we create it? And then you're now explaining how you're trying to let the software create so many, let's say, options for you. But when I was reading, the first step, the footprint step, you took samples from I think Boston's.
Yeah, absolutely.
Boston's buildings, but you didn't apply the laws of Boston's requirements to build, let's say, the offsets of the limits or something. You just took a sample of so many prints and created a new sample. Is it better if we start like looking at the laws and the regulation, or is this so hard to implement the laws inside the, say, simulation?
No, so to your point, yes, you're absolutely right. I think the weakest of the three models I have in the articles is definitely the first one, and this goes back to Lewis's question actually. The laws, the rules you're mentioning, that represents those metadata I was talking about. But the interesting thing is those rules, those side boundaries, offsets, are heuristics, right? There are rules that are descriptive. We could go the parametric way again, right? We could just model those things. But I think there's another avenue with AI is trying to approach those rules in a bottom-up fashion. I'm not saying it's the only way, but I think at least as an experiment is interesting. Those setbacks, those rules are legible in the buildings of the cities, right? If you take Boston's building, well, those rules are embedded in the forms. They're already in place. If you do this AI model training on those shapes, well, and if you do it well, and it's actually hard, and you fit in the background enough metadata, you might be able actually to circle those rules and to actually grasp those rules implicitly.
Okay.
You see what I mean?
It's like what you explained about the noise, and it's almost the 0.05 second simulation to achieve the noise quality. It's almost the same idea you're talking now, that approximately you're seeing, or let's say by visualization, you're like, taking the results. Okay.
Yeah, exactly. And there's the thing with AI that I think is really really interesting is the power of the implicit. With parametricism, we used to explicit things everywhere. We explicitly define rules. We encode only those things that we can coin down explicitly. But there's so many things about like architecture and the built environment that are completely implicit. You were talking about like regulation and offsets, for example, in the site boundaries. There's so many inconsistency to those rules that actually just following the rules, just following the heuristics that the cities puts forward in the building code would yield inconsistent results. I mean, this is super interesting. Like all the tech ventures I took part to, all of them tried to model those rules. It's a fact that those rules are meant to be broken. So I would even argue that there's better chance maybe to grasp the actual rules that underpin the city by doing this bottom-up approach, observational science, right? Like taking the data and learning from it, than trying to explicitly encode all those rules. Because by themselves, they are inconsistent. And this is across all cities, you see it. They're meant to be broken.
Yeah, thank you.
You're welcome.
Anybody else?
Sorry, can I add another question? Sorry.
Sure, go ahead.
Just I was thinking because all the, let's say, as you said now, all your work is based on, let's say, previous observations of many works and just compiling them and let this AI, let's say, learn from previous works. But if you're working with something, let's say, you don't have a lot of, let's say, info about it, or you don't have this access to this, let's say, previous information to build on it, to make it learn. So you should like make it learn by following the rules, no? Is that the logic, or am I not?
No, it's okay. It's a really fair question. Yeah, so that's a thing. There's two ways to answer this question. There's two ways. There's actually another field of, the first one is you can learn based on rules. There's another field of AI that I'm not actually really versed into, but I know quite well. I just haven't done much research in the area, which is what we call Q-learning, where you actually set in place rules and you let the machine, bounce endless examples and tries against those rules and learn from the results it gets each time. So you see, it's not really trying to learn based on a set of data points, but rather on the outcome of behaving with respect to certain rules. That field of AI is actually super interesting. Very few projects in the area. Georgia Tech has some things, Stanford also. But again, there's still a lot of things to do. So in this area, there's actually things done with AI that goes into this direction that you could look into. There's another way to answer this. It's that you don't need to have a model of the exact phenomenon you're trying to produce. There's such a thing called transfer learning. So transfer learning is, just to give you a simple example, say you want to generate pictures of cats. Well, you can either train a model for 10 hours and learn that, or you can take a model that was already trained on human faces and train it for 30 minutes on cats' pictures. And then it will make realistic looking cats. It's a stupid example, but it simply says you can transfer knowledge from one field to the other. And so if you want to generate, let's say, certain type of housing building, well, if you have a model that has been already trained on another type of housing project, and you should only have, for the type of project you wanted to learn, you only have few data points, you only have maybe 100 of them, well, you can do transfer learning. So this notion of transfer learning, there's a lot of literature on the topic. It's fascinating because it simply says expertise can be encapsulated and transferred to an adjacent field. It's really exciting as a notion.
Thanks a lot.
Yeah, no problem.
I would like to add, it's not a question, maybe just a comment, because it's really interesting. And going back to Rudy's question about the rules that we have for our buildings, well, these rules are meant to create a set of conditions, right? But maybe it's really interesting if the AI, if the rules were like intelligent. I mean, the rules were specifically for each case changing to set those conditions. And maybe it's going like the other way around. So the AI would create this set of rules. So it's so we create better designs.
So in your comment, there's the idea of somehow dynamically changing the rule set, right?
Exactly.
Yeah, that makes sense. No, then just maybe a point of reference here that can be interesting to look into, because it's actually a valid point. There's been work done on this. There are like networks that can change so AI models, but more specifically neural networks that can change the hierarchy, or I'm sorry, the architecture based on the problem it's facing. So there is also this notion that, well, a model can, mutate given certain conditions. The most simple form of mutation is simply changing the weights, so changing, let's say, the parameters of the model. But there are more drastic types of models that can actually change their own architecture, and I think that's really interesting, and maybe very relevant to what we do. That's to your point, Luis. Maybe a more general comment is that actually, going back to Rudy's comment, I've gone actually way beyond what you've seen today. I think today was really about showing you like kind of the state of things, but there's way more to be said, and also there's a way more specific discourse to have when it comes to AI in architecture specifically. And so the like all my recent work revolves around the notion of semantics, and I've posted things. I mean, there's this lecture at ETH that feel free to look into. But some articles are coming out soon about the topic. But the idea is that to be able to handle, the multiplicity of use cases in architecture, every building is a single piece, right? It's different from another. We need to come up with like a more clear framework to embed AI into our field. And I have this whole theory around semantics because I think it's the way to go. And I think you might find it interesting because it actually, gives a richer understanding of what AI is in architecture. It's not just a tool again, but also it has to be decompacted, unbundled, and matched with realities of our field. It's very fuzzy what I'm saying right now. I'm aware without the slides, it's a bit up in the air. But that thing that's coming, I think, embracing semantics, I think, is the way to go. Again, okay, I'm just going to do one thing. Can you see my screen, or?
Yeah.
Yeah. Can you see the search I'm making, or?
ETH blog.
ETH blog. Yes, absolutely. Okay, no, sorry, it's a bit hacky, but what I want to do is send you this link, because actually there's the video of, so it's a symposium where I took part to, I think it was 2 weeks ago, and after, I think I'm giving the first talk in the thing. It's like a 20-minute talk.
Oh, great.
But it's a bit harsh in terms of AI, a bit steep. But if you like the topic, I think you will find it interesting. It runs from like 9 minutes in until 30 minutes in, I think. But anyway, it was just a link and a comment. Any other thing?
It's a follow-up from today's lecture, maybe. You know, some more material that we can chew a little bit and digest.
Exactly. It's like season 2, yeah. Exactly.
No, because it's difficult to understand how AI works, because it really presents a completely new paradigm for our students and maybe for many people. The idea of not working with rules is really, I'd say, problematic. I mean, it's like, how does it do it? You know, how do we encode knowledge in this system? You know?
Yeah. And it puts you in a situation where you lose control, which is something we hate with parametrics, because everything has a set of components and has a slider. If you don't have that, you feel powerless. And so it requires from us to accept a certain looseness in the model, but a more holistic approach to the result we're trying to get.
And it's funny because it's in a way back to the black box. I mean, you design the system that learns, you teach it, but it really is a sort of black box because you don't understand very well what it is doing inside. While with the rules, it's the opposite.
So to that very specific point, it's perfect you said that, because yes, today, actually that's something you'll see in the presentation I sent in the link. Today we are at the transition phase. We are very much into a black box situation. We use models that don't allow us any control, not much. We can condition them by inputting things, and then we get some form of output, and we're stuck with in-out. Okay, but now there's a new generation of AI models and a whole new concept that came out, which is the notion of latent space. There's an in-between space between input and output, which lies at the heart of the model, and that we can actually control. And that control gives us back the control that we once liked in parametricism. So a latent approach to architecture, that is to say, using AI model that have the latent space and shaping those latent space to our wish, basically brings back the notion of white box. So it's never going to be a white box. It's going to be, so it's not from me.
More transparent box.
Well, it's a gray box. So it's Underwood, the professor I work with at Harvard, has this whole theory around this. It's a gray box. Like you can put inputs, you can tweak what's happening during the generation process, but you don't have a full control as you used to do with parametricism. But what you gain out of it is the quality of what's getting out. It's just way beyond.
Okay. And just as a sort of a last question for you, maybe, or last suggestion. Our students have been working with basically parametricism, rules, programming. What is a good way to get introduced into artificial intelligence? Is there a package, a little program, something that they could experiment by themselves? Some of what you have been showing.
Yeah, of course. So I think the easiest way to get in this world is to look into. So let's talk about two things. There's the format. How does it look like? And then there is like the tools that get in there. So for the formats, the best way to get in there is to use notebooks. So notebooks are these things. You can download Jupyter, and then out of Jupyter you can just have a notebook, which is basically an interface where you can code. The language is Python, and you can then import libraries in there, the same way you could import components in Grasshopper. As for the libraries in there, I think experimenting with TensorFlow is the best way. There's like endless tutorials on TensorFlow's website that shows you. So those are applications that are not at all applied to architecture, but it's a healthy thing, to be frank with you, because I think it's something that comes from outside, and then once we master it, it helps us reinterrogate our field, rather than taking already baked ideas and then being stuck in the box because we didn't come up with anything. So again, downloading this Jupyter Notebook thing, learning Python, then getting acquainted with TensorFlow. It's like the framework from Google to do machine learning, and then last step is just looking into research papers. So ArchiveX is like the website by Cornell where all those research papers are posted. It's just a public repo of papers, and there's so many amazing papers on the topic. Again, there's a few that came out recently. HouseGAN is one, Graph2Plan is another. Those are like machine learning research project with code available applied to architecture, and they are open. You can just play with it. So yeah, no, there's lots of things you can do to get acquainted with real fast.
Okay. So let me just give a quick tour around if anybody else wants to ask something or even chat with our guest.
Yeah, hi.
Hello.
Hello.
Hi.
Yeah, so I mean, just like I said, I realized that AI is far from being perfect yet. But in the next 5 to even 100 years, when an AI is able to, completely design, let's say, the next pyramids, what do you think of the authorship situation there?
Right. So the thing with that is that unless I see it, I won't believe it. At least that's for myself. The truth with AI model is that they won't. We don't see them doing that anytime soon. So even when you say 100 years, maybe then we can talk about faith. But if we stay within the realm of rationality, well, there's no proof is never going to be able to do all the things we do as architects. And that's not talking from outside of AI. It's really me saying this within, talking from inside, like knowing how it looks like from the inside. The point of AI was to somehow emulate some of our faculties, and it's very clear that it, can do the easiest one, but all the judgment calls we make every day, that is just way beyond AI. So the question today, to be frank with you, is really not too much about the authorship. And I know you wanted an answer on this one, but the question about the authorship comes if there is a possibility for AI to replace us, which I think is not a thing. The question is way more about the business models. So that's the more pragmatic answer. If the question of the threat is, the one to answer, it's not so much is AI, the technology, going to replace us? Is more, what are those business models that are going to be bundled with AI that can actually change our discipline? That is a way more relevant, I think, approach to the question. Does that answer your question?
Yeah, it does. It does.
Awesome.
Okay.
I have one question. How we can apply the artificial intelligence to create a better relationship between the architecture and the environment? I mean, is possible that help us to improve this relationship? I think maybe showing the best cases we have or compare it with the worst cases. I think the output maybe will be interesting, or maybe I'm too innocent.
So to be clear, your question is, how can we have AI contribute to the environmental question? Is that right?
Yes.
Yeah. Okay. Yeah. So no. Actually, it's again a very valid question, because I haven't been showing anything about that here, but it's true that what AI also does really well is to handle the correlation between phenomena. So one correlation that is important is the relationship between a building and its environment, and how those two things correlate. Actually, it's interesting to think of it as a correlation, because it's not always easy to coin down what is the impact of a building on the environment. Like even if we know the big trade-offs, it's not always easy to grasp fully the the full range of effects and push and pull between the environment and the building and the building and the environment. So AI is actually great at, I think, at modeling those implicit relationships. And when it comes to environment, it's a very good, I think, avenue to look into, because it's very much an implicit field or notion. AI can do a lot about it. It comes down also to the notion of data collection. Can you get data on the topic? How hard would it be? And what kind of data do you need to grasp this relationship between AI and its between architecture and its environment? That is for the big picture. But there are very tangible things though that are way more easy to see also today. You've seen those structures in the presentation. Those structures, one of the key performance metrics was I think in English say tonnage, so the weight of steel of the structure. And one point of the model was to minimize the amount of steel in the structure. And AI actually does well at those questions. It's able pretty well to handle those performance questions. So you see, if you tie AI to simple things like weight of steel of a structure, then there are clear pathways today to actually use AI in that purpose. But there's a bigger picture, I think, which is implicit tie between building and the environment that should be modeled, and I think AI can do. I don't think heuristics or descriptive techniques can grasp the full range of interaction between buildings and their environment. But again, Danny, I don't know if that answers your question.
Yes, thank you. I think that are good news.
Yeah, it is. Absolutely.
Okay. Well, I think that it's time to wrap up.
Sounds good.
Even though we started a little bit later due to uncontrolled events that I don't still I haven't still understood, but let's forget that. No, I just wanted to use the last minute to thank you, Stanislas, for such a great introduction to this topic. I think everybody can now see that in their work, artificial intelligence is a key element that has to be considered beyond the sheer programming that they are doing with the usual tools, with Grasshopper and other parametric tools. So probably approaching AI with an open mind is interesting, because lots of things can be done. Probably many more than the ones that you have showed us. Mm-hmm. But I think that it's another tool that has to come into everybody's tool set for design for these designs for these digital designs. So thank you very much, Gerard. Thank you. I don't know if you want to say anything, but
no, just thank you again, Stanislas. I think that's been very inspiring, and this is a topic that some alumni of this master have been working on. Tai, for instance, who is here attending this lecture, and I think that has plenty of potential. In the forthcoming years, we are going to see much more applications of AI applied. I think that in the lecture you have pointed to simulation, just to speed up, just to a way of providing drafts for simulating processes, no? Maybe with less accuracy, but of course with much more faster than the usual processes. And I'm personally really interested, and I think that we can further collaborate on this in the future. So thank you so much for accepting the invitation, and it's been a pleasure.
My pleasure. Thanks, everyone.
Thank you very much. Thank you, everybody.
Thank you.
Thank you.
Thank you.
See you next week.
Thank you so much.